Hi everybody, this is Mechanical Engineering by Hand, and in this video I'll talk about pipe head loss. And I want to talk about the situation where you know the elevation change of the water. In this case, we're looking at a reservoir with water at 60 degrees, and the top of the water, or the water surface, is at 300 feet, and then it discharges at 0 feet. So our change in elevation is 300 feet, and the head we have pushing on the water is 300 feet. And so the head loss is going to be 300 feet. And we can use that to calculate the flow rate. So we have a few things going on here. We have the pipe itself, which is 24-inch ID HDPE, and it's 2 miles long. And then I've got the specific roughness there, and then this is the kinematic viscosity of the water. Another thing is we have a reentrant, and that's anytime the pipe sticks into the water supply like that. There's a K value associated with that. There's a K value associated with this globe valve. And anytime you look up K values or equivalent lengths for valves, it is assuming they're 100% open. So this globe valve is 100% open. And then there's also a K value associated with this water when it discharges out into the atmosphere. So let's look at this. We will use this equation, which is head loss in feet is equal to friction factor times the length times velocity squared divided by 2, diameter, and gravity. So we know what the head loss is going to be. It's going to be our 300 feet. 300 feet equals F times the length, which is 10,560 feet, times velocity squared over 2 times our diameter, which is 2 feet, times gravity. And when you simplify this, that works out to 82 FV squared. Okay, and then this entrance into the pipe, it's called a reentrant when it sticks into the water like that. So we'll look up that K value, reentrant, and the head loss using the K value is K times V squared over 2G. So I'm going to look that up in this book. And they have, they call it a pipe entrance. Most books would call this a reentrant. And for all pipe sizes, the K value is 0.78. So we have 0.78 times V squared over 64.4, which is equal to, which is equal to V squared over 82.6. Okay, and then the globe valve. I'll look up the K value for that in the same book. And they have globe valves listed here, and the K value for 24-inch is 4.1. And they also give length over diameter, which is used to convert that to an equivalent length of straight pipe. So if we were to use that method, we would multiply 340 times 2, and we would get 680. So that globe valve, when it's 100% open, is equivalent to 680 feet of pipe. So just remember that anytime you see a globe valve, make sure you include that head loss because it's usually significant. Okay, so our K value was 4.1, V squared over 64.4, and that equals V squared over 15.7. And then the exit, these are always easy to remember because they're 1, but I'll show you where they list it. Right here, a pipe entrance doesn't matter, or sorry, let's see, pipe exit doesn't matter what shape it has. For all pipe sizes, the K value is 1. So K is 1, and then we have V squared over 64.4, so that equals V squared over 64.4. And then when we're what we're going to do is make an assumption on our velocity and then check to see if we're right. So it would be helpful to combine these. So we just add these, and when we do that, we get V squared over 10.95. Okay, so now we have everything. We have this for the pipe itself, and then this for the valve entrance and exit. So let me write that over here. 300 feet equals 82 F V squared plus this V squared over 10.95, and then we'll return back to this equation when we check our assumptions. So let's take a first guess and say that our velocity is 10 feet per second. Okay, and we need to calculate the Reynolds number, which is diameter velocity over kinematic viscosity. So that equals 2 times 10 over 0.00001217, and that equals 1.6 times 10 to the 6, so 1.6 million. And we also need to calculate the relative roughness, E over D. So that was 5 times 10 to the negative 6 over 2, which is 2.5 times 10 to the negative 6. Okay, so I'll look in this book at this Moody chart, and there are Moody charts in other books, but I like this book, and so let's see, we found our Reynolds number, which is 1.6 million. That will be right about here. And then our relative roughness is so low that I'm just going to use this line that they call smooth pipes, which is the bottom line. So we'll go up to where 1.6 and that line cross and go over, and it looks like that would be 0.0105 for the friction factor. So we'll use that. Okay, so for this guess, F equals 0.0105. Okay. Now we can use this equation to see if we're correct on that guess. So 300 equals 82 times 0.0105 times 10 squared plus 10 squared over 10.95, and that equals 95 feet. So we're off quite a bit. Now, because this flow rate is dependent on, this head loss depends on the flow rate squared, we can take a ratio of this and what we want, and then just take the square root to estimate a new guess. So what I mean by that is we'll take this ratio, our velocity needs to be higher, so 300 over 95, and take the square root of that, and then we'll multiply it times our first guess, which was 10 feet per second. And so that equals 17.8 feet per second. Okay, so now we calculate our Reynolds number, and that is 2.9 times 10 to the 6th. Go back to our Moody chart. 2.9, we're basically on 3 million at that point, which is right here, and we'll go up to that bottom line and then go over, and I'm going to say that is 0.0098. So that's our new friction factor. Okay, and now we recalculate this again to see if our new guess is correct. 300 300 feet equals 82 times 0.0098 times our new velocity squared plus 17.8 squared over 10.95, and that equals 284 feet. So you can see how much closer we are to 300 feet. We went from 95 to 284 just using that method. So I'm going to do that one more time, but I'm not going to recalculate to see if it's correct, because I think it would be close enough. So, by the way, if you have someone checking your work, you should probably cross these off so they don't think you're crazy. And I'll use this method again. Guess what we want over our last answer, take the square root of that times our last guess of 17.8, and that is 18.3 feet per second. Okay, so let's see, to calculate the GPM, we need to know the area of this pipe, which is pi r squared. So A equals pi times 1, and then the flow rate would just be the area times our velocity. So pi times 18.3 is 57.5 cubic feet per second, and then converting that to GPM is 25,800. So that would be our flow rate through this 2-foot diameter HDPE pipe with a globe valve on the end that's 100% open, and we have 300 feet of pressure pushing on it. I hope that was helpful. Thank you for watching.